My name is Xiaoliang Ma. I'm presenting to you the iHorse project. iHorse stands for Improving Air Quality and Health Risk Forecasting by Data-Driven Modeling of Traffic and Atmospheric Environments. The project is a Digital Futures demonstration project. It is a collaboration between the Stockholm University, the Royal Institute of Technology, and the Environmental Administration of the Stockholm City. This is our project team. Three senior researchers have been involved in this project. And the PI is Christer Johansson, who is a professor in environmental physics in Stockholm University. And myself is a docent in intelligent transportation system at KTH. Magnus Ungaut, who is a docent in meteorology and works for the environmental administration of Stockholm City. Air pollution is so far considered by scientists as the largest environmental health risk to human beings, especially for people living in city. It is known that air pollution has a direct relation with respiratory and cardiovascular diseases. The mortality of these diseases is quantified as globally 4.5 million deaths per year. Because of the air pollution impacts, people may want to know what are the health risks of breathing the air today and tomorrow. The Environmental Administration of Stockholm City has been developing an air pollution prediction system during the past few years. And the system provides hourly information on health risk of the coming few days down to the street level. Since 2021, a mobile app has been online providing forecasting services of the air quality and health risk indexes to the general public, especially for residents in the Stockholm area. Using this information, individuals can adapt their health diary in advance. The forecasts of AQHI are based on a number of input factors. CAM's AQ forecast and the pollen forecast, they are the regional concentration values of the air pollutants and pollen. Meteorology and meteorology forecast is another factor that may impact the AQHI forecast dramatically. AQ forecast for the city stands for the contribution from the air pollution generated locally, especially the road traffic emissions generated on the street. Air quality monitor data from a number of stations in the city has been used to calibrate and validate the AQHI forecast. There are two major objectives for this project. The first is to improve the accuracy of the forecast of health risk associated with air pollution. In other words, we want to improve the air quality and health risk indexes, or AQHI indexes for the city. The second objective is to improve the forecast of traffic-induced emissions and air pollution impacts. Conventionally, both traffic modeling and air pollution modeling involves very complex physical models. But how can we improve these models? With the increasing deployment of different types of sensors for measuring traffic, for measuring the environment, and we consider that we can use data-driven machine learning approaches to improve the AQHI prediction. Therefore, we can improve the air pollution prediction system run by Stockholm City. In order to improve the AQHI prediction for Stockholm area using a data-driven approach, this study applied air quality data measured at 3 street sites and 1 rooftop site in central Stockholm. Precision equipment has been used in the data collection procedure. For 3 street sites, PM10, NO2, and NOx are the air pollutants being measured. They are considered to be generated from mainly road traffic. And for the one rooftop site in Sodom, PM10, NO2, NOx, and O3 are measured, and these pollutants are considered to be transported from other regions to Stockholm. Different machine learning models have been applied in the iHorse study. And according to our initial data analysis, we find air quality data also shows some periodicity property for hour, for day, for week. Therefore, two tree-like models, one is called random forest, another is a gradient boosting model, has been applied in our study. And in addition to these two conventional modeling approaches, we also include one deep learning model called the long short-term memory model, and its variation, BLSTM model, has been applied in our study for predicting the air pollution. And the LSTM model has a good reputation in modeling the time series data. The input data for the machine learning models can include three categories. The first category is a deterministic forecast from the physical models, and this includes NOx, PM10 concentrations, and the CAMS and the local forecasts, and also the AQHI prediction calculated from the NOx, PM10, and ozone. And meteorology variables are another type of prediction variables being used. And this include wind direction, wind speed, relative humidity, and the temperature, pressure, and precipitation, and so on. And the second category of the input data is include the measurement data itself. Since it depends on the prediction horizon, we simply use the lagged measurement data. For example, if we have the prediction horizon of 24 hours, then the hourly mean concentration one day before is considered as input data. Of course, we also enrich the features of the measurement data, the lagged measurement data. For example, the maximum the hourly mean concentration of the last 24 hours, and also some percentiles features has been used as an input data. The third category of the input data is calendar data. This includes hourly day, hour of the day, and the day of the year, the weekday, and so on. These slides give you some example result on the prediction of NOx by a random forest model and the deterministic forecast model. In the picture of the lower left, you can see that the hourly prediction pattern by the two models aggregated over all days. And obviously, the random forest prediction pattern generally follows observations. And whereas the deterministic forecast model has certain deviation from the observations, especially after 12 o'clock, and it has a big deviation from the observation values. And in the upper left picture, and the prediction pattern is even aggregated over different weekdays. Therefore, you can see how the deterministic model is different from the observations in different weekdays. On the other hand, generally the random forest model follows the observations for different weekdays. The rightmost two pictures shows the linear regression result of the observation and the prediction by different models. And the upper one is for the deterministic prediction. The lower one is for the random forest prediction. The linear regression for the random forest prediction and has a larger R-square value, actually much larger square value compared to deterministic model. It shows its prediction advantages on the observation data. This slide shows experimental result of one-day prediction of NOx by all three machine learning models at certain test sites. And the test data is between July 2021 until December of 2021, almost a half-year data. And all three models achieves a similar prediction performance. And there's in fact no single model that can beat overwhelmingly the other two models for all test sites. And on the other hand, you can see that in this picture that some of the peak values in the observation cannot be captured by all three models, which indicate that the training data may not contain such kind of pattern. So to summarize, and iHorse has applied machine learning models to improve the air quality forecast substantially for all pollutants and the health risk index for both street and urban background air pollution prediction. And currently we are implementing the machine learning method that developed in this project in the current air quality forecast system in Stockholm, and to demonstrate the improvement. And there is still potential to improve the machine learning models. And we also expect some more conference and journal publications and based on our research. And the future of this air pollution prediction system is very promising. It is very likely this such kind of system will be tested and implemented in other cities in the EU countries.